And we're here. Hello. Good morning, good afternoon, good evening. Something's getting updated. Okay. I think that's why the app just closed on itself. Hi. Hello. I started a bit late today, so sorry about that. But I think, I started this stream a bit late, but I think we're starting on time compared to the other days. Okay. I am ready, so good morning, Mustafa. Thank you for being here. Yes. I think we're ready to just continue where we left off yesterday, which was, if I just share my screen, you will see that I have this opened, but I think we almost ended here. Did I close? No, I did not. Here's the video. So we were in the beginning of lesson 2, just looking at random forests and evaluation metrics, the loveliest thing to do first thing in the morning, right? I think my internet is bearable. It's not great, but it's bearable. I really like those glasses she's wearing. Okay. So let's play the video and see where that takes us. Evaluation metrics. I'll go back just a few seconds. Okay.
Kind of how you got it there, it's going to work.
Okay.
Great. Okay, so then we had all of our data for Blue Books for Bulldozers competition in data/bulldozers, and here it is, right? So we were able to read that CSV file. The only thing we really had to do was to say which columns were dates. And having done that, we were able to take a look at a few of the examples of the rows of the data.
Okay, we're going over what we did. Thank you. I also like how the headphones match the clothes. The app gives you a lot of choices, so it's always fun to change things and clothes. Oh, hello. Yes. What happened? Should I watch it on YouTube? Would that be easier? Let's do that. Come on, the internet isn't this bad. You're making fun of me. There.
And so we also...
Oh, I like the panda emoji. I used to be called a panda. Anyway.
Also noted that it's very important to deeply understand the evaluation metric for this project. And so for Kaggle, they tell you what the evaluation metric is. And in this case, it was the root mean squared log error. So that is
squared log error. What is that?
The sum of the actuals minus the predictions.
Actual minus prediction. Okay.
Right? But it's the log of the actuals minus the log of the predictions squared.
Mean squared log error. I think so, yes. It was written like that.
Right? So if we replace actuals with log actuals and replace predictions with log predictions, then it's just the same as root mean squared error.
What happened to the R? God.
So that's what we did. was we replaced sale price with log of sale price. And so now, if we optimize for root mean squared error, we're actually optimizing for the root mean squared error of the logs. Okay? So then we learnt that we need all of our columns to be numbers. And so the first way we did that was to take the date column and remove it, and instead replace it with a whole bunch of different columns. Such as, is that date the start of a quarter? Is it the end of a year? How many days are elapsed since January the 1st, 1970? What's the year? What's the month? What's the day of week? And so forth. Okay, so they're all numbers.
I think you don't need to do the square root because the output of the random forest is already a mean squared error, but the logging is the extra part. I think the mean square error is like a normal thing, so that's why you don't need the. Do you mean because of the root? Not sure.
Then we learnt that we can use train_cats to replace all of the strings with categories. Now when you do that, it doesn't look like you've done anything different. They still look like strings, right? But if you actually take a deeper look, you'll see that the data type now is not string but category. And category is a pandas class where you can then go .cat dot and find a whole bunch of different attributes, such as cat.categories to find a list of all of the possible categories. And this says high is going to become 0, low will become 1, medium will become 2. So we can then get codes to actually get the numbers. So then what we need to do to actually use this data set to turn it into numbers is take every categorical column and replace it with cat.codes. And so we did that using procdf. Okay. So how do I get the source code for procdf?
It should have an extension of read mean error and root mean squared error. I guess, yes. I guess they're normal. I mean, I learned about them recently, but yeah.
Question mark. Okay. All right, so if I scroll down, I go through each column and I numericalize it. Okay, that's actually the one I want. So I'm going to now have to look up numericalize. So tab to complete it. If it's not numeric, then replace the data frames field with that columns.cat.codes plus 1, because otherwise unknown is -1. We want unknown to be 0. Okay? So that's how we turn the strings into numbers. Right? They get replaced with a unique, basically arbitrary.
He did say fast.ai is a really opinionated library, and just the fact that he's made the +1 for -1s not being unknown but 0, that's quite opinionated, isn't it? Like, what if I want my zeros to be a normal thing like every list out there? Why should it be unknown?
The index. It's actually based on the alphabetical order of the feature names. The other thing procdf did, remember, was continuous columns that had missing values. The missing got replaced with the median, and we added an additional column called column name _NA, which is a Boolean column, told you if that particular item was missing or not. So once we did that, we were able to call random forest regressor dot fit and get the dot score, and it turns out we have an R squared of 0.98. Can anybody tell me what an R squared is?
The difference of the
Melissa,
actual
you want to tell me?
minus predicted.
Yeah, it's, I'll help Marsha.
Okay.
Maybe you need to dig into the underlying code and see how it was implemented so that you can implement another approach. Not yet, but why not? Maybe. I don't think I'm there yet in understanding, but yeah, you're right. The fact that the library chooses for you instead of you, that could, you may need to like say, I see your point.
So R squared essentially shows how much variance is explained by the model. This is the this is the relation of this is SSR, which is like trying to remember the exact formula, but like
I mean, roughly, intuitively.
Yeah, intuitively, it's how much the model explains how much it accounts for the variance in the data.
Okay, good. So let's talk about the formula. And so with formulas, the idea is not to learn the formula and remember it, but to learn what the formula does and understand it, right? So here's the formula.
I like his teaching style
It's
a lot.
1 minus something divided by something else.
Okay.
So what's the something else on the bottom? SS tot. Okay, so what this is saying is we've got some actual data, some YIs, right? We've got some actual data. 3, 2, 4, 1.
Target
Okay.
column.
And then we've got some average. Okay, so our top bit, this SS tot, is the sum of each of these minus that. So in other words, it's telling us how much does this data vary. But perhaps more interestingly is, remember when we talked about, like, last week, what's the simplest non-stupid model you could come up with?
Random
And I think the
forest?
simplest non-stupid model we came up with was create a column of the mean. Just copy the mean a bunch of times and submit that to Kaggle.
A column that's not non-data. And if it's continuous, then we put the mean everywhere where it was empty.
If you did that, then your root mean squared error would be this. So this is the root mean squared.
Is that a... What is that? Variance formula. I might not be sigma, okay. I don't think I remember it. Or maybe I haven't even studied it. I googled it. Otherwise I didn't know.
Squared error of the most naive, non-stupid model, where the model is just predict the mean. On the top, we have SS res, which is here, which is that we're now going to add a column of predictions. Okay, and so now what we do is, rather than taking the yi minus y mean, we're going to take yi.
So It is the variance formula based on what you're saying? The difference between variance and standard deviation is square root. My math is weak.
Minus fi, right? And so now instead of saying, what's the root mean squared error of our naive model, we're saying, what's the root mean squared error of the actual model that we're interested in? And then we take the ratio. So in other words, if we actually were exactly as effective as just predicting the mean, then this would be, top and bottom would be the same. That would be 1. 1 minus 1 would be 0.
So no deviation.
If we were perfect, so fi minus yi was always 0, then that's 0 divided by something. 1 minus that is 1. Okay, so what is the possible range of values of r squared?
From 0 to 1?
Okay, I heard a lot of 0 to 1. Does anybody want to give me an alternative? Negative 1 to 1?
Anything less than 1.
Huh?
Anything less than 1.
Anything less than 1. There's the right answer. Let's find out why.
Oh, because it can be as big as it wants. Okay, so why is it any number less than 1?
Because you can make a model basically as crappy as you want, and just like get as like big errors as you want, and you're just subtracting from 1 in the formula. So.
Exactly. So interestingly, I was talking to our computer science professor, Terence, this morning, who was talking to a statistics professor, told him that the possible range of values was r squared was 0 to 1. And I said, that is totally not true. If you predict infinity for every column, for every row, then you're going to have infinity for every residual, and so you're going to have 1 minus infinity. Okay, so the possible range of values is less than 1. That's all we know.
Wow, yeah. But yeah, this number can be as big as it wants, like you said, infinity, so wow, that's cool.
And this will happen. You will get negative values sometimes in your r squared. And when that happens, it's not a mistake, it's not like a bug, it means your model is worse than predicting the mean. Okay, which suggests it's not great. So that's r squared. It's not necessarily what you're actually trying to optimize, right? But it's the nice thing about it is that it's a number that you can use kind of for every model, and so you.
Yeah, I think my mind was also blown.
You can kind of start to try to get a feel of like, what does 0.8 look like? What does 0.9 look like? So like something I find interesting is to like create some different synthetic data sets, just two dimensions, with kind of different amounts of random noise, and like see what they look like on a scatter plot and see what their r squared are, just to kind of get a feel for like, what is an r squared? Is an r squared of 0.9 close or not? What about 0.7, close or not? Okay, so I think r squared is a useful number to have a familiarity with, and you don't need to remember the formula if you remember the meaning, which is what's the ratio between how good your model is, root mean squared error, versus how good is the naive mean model, root squared error. Okay, in our case, 0.98, it's saying it's a very good model. However, it might be a very good model because it looks like this, right? And this would be called overfitting. So we may well have created a model which is very good at running through the points that we gave it, but it's not going to be very good at running through points that we didn't give it. So that's why we always want to have a validation set. Creating your validation set is the most important thing that I think you need to do when you're doing a machine learning project, at least in terms of in the actual modeling part. Because what you need to
when you have like over 95, you're like, I messed up.
do is come up with a data set where the score of your model on that data set is going to be representative of how well your model is going to do in the real world, like in Kaggle on the leaderboard or off Kaggle, like when you actually use it in production. I very, very, very often hear people in industry say, I don't trust machine learning. I tried modeling once. It looked great. We put it in production. It didn't work. Now, whose fault is that, right? That means their validation set was not representative. Right? So here's a very simple thing, which generally speaking, Kaggle is pretty good about doing. If your data has a time piece in it, right, as happens in Blue Book for Bulldozers. In Blue Book for Bulldozers, we're talking about the sale price of a piece of industrial equipment on a particular date. So the startup doing this competition wanted to create a model that wouldn't predict last February's prices, but would predict next month's prices. So what they did was they gave us data representing a particular date range in the training set, and then the test set represented a future set of dates that wasn't represented in the training.
If you have a time series, you can split by date instead of randomly. So until now, or even if the time set is in the past, you can still split it based on the time, right?
Set, right? So that's pretty good, right? That means that if
we have the same, right?
doing well on this model, we've built something which can actually predict the future, or at least it could predict the future then, assuming things haven't changed dramatically. So that's the test set we have. So we need to create a validation set that has the same properties.
Agreed.
So the test set had 12,000 rows in. So let's create a validation set that has 12,000 rows.
Right.
And then let's split the data set into the first n minus 12,000 rows for the training set, and the last 12,000 rows for the validation set. And so we've now got something which hopefully looks like Kaggle's test set, close enough that when we actually try and use this validation set, we're going to get some reasonably accurate scores. And the reason we want this is because on Kaggle, you can only submit so many times. And if you submit too often, you'll end up overfitting to the leaderboard anyway. And in real life, you actually want to build a model that's going to work in real life. Did you have a question? Can we have the green box, please?
Can you explain the difference between a validation set and a test set?
Absolutely. So what we're going to learn today is how to set, one of the things we'll learn is how to set hyperparameters. Hyperparameters are like tuning parameters that are going to change how your model behaves. Now, if you just have one holdout set, so one set of data that you're not using to train with, and we use that to decide which set of hyperparameters to use, if we try 1,000 different sets of hyperparameters, we may end up overfitting to that holdout set. That is to say, we'll find something which only accidentally worked. So what we actually want to do is we want to have a second holdout set where we can say, okay, I'm finished. Okay, I've done the best I can. And now just once, right at the end, I'm going to see whether it works. And so this is something which almost nobody in industry does correctly. You really actually need to remove that holdout set, and that's called the test set. Remove it from the data, give it to somebody else, and tell them, do not let me look at this data until I promise you I'm finished. Like, it's so hard otherwise not to look at it. And for example, in the world of psychology and sociology, you might have heard about this replication crisis. And this is basically because people in these fields have accidentally, or intentionally maybe, been p-hacking, which means they've been basically trying lots of different variations until they find something that works. And then it turns out when they try to replicate it, in other words, it's like somebody creates a test set. Somebody says, okay, this study which shows, the impact of whether you eat marshmallows on your tenacity later in life, I'm going to rerun it, and like over half the time, they're finding the effect turns out not to exist. So that's why we want to have a test set.
Validation set and also test set. Okay.
So for handling categorical data, you converted those to numerics, to numbers, ordered numbers. I've seen a lot of models where we convert categorical data into different columns using one hot encoding.
Yes.
So which approach to use in which model?
Yeah, we're going to tackle that today. Yeah, it's a great question. Okay, so I'm splitting my my data into validation and training sets, and so you can see now that my validation set is 12,000 by 66, whereas my training set is 389,000 by 66. Okay, so we're going to use this set of data to train a model, and this set of data to see how well it's working. So when we then tried that last week, we found out, just a moment, we found out that our model, which had 0.982 R squared on the training set, only had 0.887 on the validation set, which makes us think that we're overfitting quite badly. But it turned out it wasn't too badly, because the root mean squared error on the logs of the prices actually would have put us in the top 25% of the competition anyway. So even although we're overfitting, it wasn't the end of the world. Could you pass the microphone to Marsha, please?
In terms of dividing the set into training and validation, it seems like you simply take the first and train observations of the data set and set them aside. Why don't you randomly pick up the observations?
Because if I did that, I wouldn't be replicating the test set. So Kaggle has a test set that when you actually look at the dates in the test set, they are a set of dates that are more recent than any date in the training set. So if we used a validation set that was a random sample, that is much easier, because we're predicting auctions, like what's the value of this piece of industrial equipment on this day, when we actually already have some observations from that day. So in general, anytime you're building a model that has a time element, you want your test set to be a separate time period, and therefore you really need your validation set to be a separate time period as well. And in this case, the data was already sorted, so that's why this works.
Yeah, that's true.
I
We've
just
got one more question over there.
forgot this time series.
Sure.
There are times where the data you have isn't sorted, so you have to sort it and then split it by time series.
So let's say we have our test, the training set where we train the data, and then we have the validation set against which we are trying to find the R square. In case our R square turns out to be really bad, we would want to tune our parameters and run it again.
Yes.
So wouldn't that be eventually overfitting on the overall training set?
Yeah, so actually that's the issue. So that would eventually have the possibility of overfitting on the validation set, and then when we try it on the test set or we submit it to Kaggle, it turns out not to be very good. And this happens in Kaggle competition.
Such a balancing act of doing your best for it to work, but also not overfitting, right?
All the time. Kaggle actually has a fourth data set, which is called the private leaderboard set. And every time you submit to Kaggle, you actually only get feedback on how well it does on something called the public leaderboard set, and you don't know which rows they are. And at the end of the competition, you actually get judged on a different data set entirely, called the private leaderboard set. So the only way to avoid this is to actually be a good machine learning practitioner and know how to set these parameters as effectively as possible, which we're going to be doing partly today and over the next few weeks. Can you get the, actually, why don't you throw it?
It would be cool if we
Is
actually...
it too early or late to ask, what's the difference between a hyperparameter and a parameter?
Too early.
Okay.
He said too late? It's really cool that the students ask questions, because like on a normal course no one would ask questions, so this is more helpful. Yeah, let's see. Some people cheat and include the public test set in their training data. Wow! To avoid this problem, I didn't know that. So they need to have a private testing set. modern problem require modern solutions, I suppose.
So let's start tracking things on root mean squared error. So here is root mean squared error in a line of code. And you can see here, like, this is one of these examples where I'm not...
Base model. This one's for you. You asked where's the square root.
Writing this the way a proper software engineer would write this, right? So a proper software engineer would be a number of things differently. They would have it on a different line.
100%.
They would
100%.
use longer variable names.
Yes, obviously. We have to be proper.
They would have documentation.
Yeah, that's cute.
Blah, blah, blah. Right? But...
blah, blah, blah. You call documentation
I really
blah,
think,
blah, blah.
like for me, I really think...
I never write documentation, but do not blah, blah, blah it.
that being able to look at something in one go with your eyes and like over time learn to immediately see what's going on has a lot of value. And also
it's cool seeing this like how it is and not just talking about it as a mythical thing.
So to like consistently use like particular letters to mean particular things or abbreviations, I think works really well in data science. If you're doing it like a take-home interview,
I don't know if it was removed, but I think it was embedded in the function. Maybe, I don't know.
You test or something. You should write your code according to PEP 8 standards, right? So PEP 8 is the style guide for Python code, and you should know it and use it because a lot of software engineers are super anal about this kind of thing. But for your own work, you know, I think this works well for me, you know. So I just wanted to make you aware, that you shouldn't necessarily...
I know. I'm just saying do not blah blah this. I'm kidding. I'm being, like he said, I'm being butthurt about it, but no. When you want something to just work, you just write whatever thing you can, you know.
I use this as a role model for dealing with software engineers, but B, that I actually think this is a reasonable approach. Okay, so there's our root mean squared error, and then from time to time we're just going to print out the score, which will give us the RMSE of the predictions on the training versus the actual, the predictions on the valid versus the actual RMSE, the R squared for the training, and the R squared for the valid. And we'll come back to OOB in a moment. So when we ran that, we found that this RMSE...
This is what we were looking at the other day, still in lesson 1, where we didn't know what the print score was, but this is what it was. Like, the other day we went through all of this, and now I feel like the kind of student that studied the material before the class, which makes me feel cool.
C was in the top 25%, and it's like, okay, there's a good start. Now, this took 8 seconds of wall time, so 8 actual seconds. If you put %time, it'll tell you how long things took. And luckily, I've got quite a few cores, quite a few CPUs in this computer, because it actually took over a minute of compute time. So it parallelized that across cores. If your data set was bigger or you had less cores, you could well find that this took a few minutes to run or even a few hours. My rule of thumb is that if something takes more than 10 seconds to run, it's too long for me to do like interactive analysis with it, right? I want to be able to like run something, wait a moment, and then continue. So what we do is we try to make sure that things can run in a reasonable time. And then when we're finished at the end of the day, we can then say, okay, this feature engineering, these hyperparameters, whatever, these are all working well, and I'll now rerun it, the big, slow, precise way. So one way to speed things up is to pass in the subset parameter to procdf.
I didn't realize the emoji becomes an emoji. I didn't mean to be this angry in the emoji. I meant to be a normal angry. There, this one works. A normal angry. There.
You know, the big, slow, precise way. So one way to speed things up is to pass in the subset parameter to procdf, and that will randomly sample my data, right?
Oh.
And so here I'm going to randomly sample 30,000 rows. Now, when I do that, I still need to be careful to make sure that my validation set doesn't change and that my training set doesn't overlap with the dates. Otherwise, I'm cheating. So I call split vals again to again do this split by dates. And you'll also see I'm using, rather than putting it into a validation set, I'm putting it into a variable called underscore. This is kind of a standard approach in Python, is to use a variable called underscore if you want to throw something away, because I don't want to change my validation set. Like, no matter what different models I build, I want to be able to compare them all to each other, so I want to keep my validation set the same all the time. Okay? So all I'm doing here is I'm resampling my training set into a the first 20,000 out of a 30,000 subset. So I now can run that, and it runs in 621 milliseconds, so I can like really zip through things now.
Just getting a subset to make it faster. Okay.
So with that, let's use this subset to build a model that is so simple that we can actually take a look at it. And so we're going to build a forest that's made of trees. And so before we look at the forest,
panic come.
We'll look at the trees. In scikit-learn, they don't call them trees, they call them estimators. So we're going to pass in the parameter number of estimators equals 1 to create a forest with just one tree in. And then we're going to make a small tree. So we pass in maximum depth equals 3. And a random forest, as we're going to learn, randomizes a whole bunch of things. We want to turn that off. So to turn that off, you say bootstrap equals false. So if I pass in these parameters, it creates a small deterministic tree. Okay, so if I fit it and say print score, my R squared has gone down from 0.85 to 0.4. So this is not a good model. It's better than the mean model. This is better than 0, right? But it's not a good model. But it's a model that we can draw. Right? So let's learn about what it's built.
Okay.
So a tree consists of a sequence of binary decisions, of binary splits. So it first of all decided to split on coupler system greater than or less than 0.5. That's a Boolean variable, so it's actually true or false. And then within the group where coupler system was true, it decided to split into year made greater than or less than 1987. And then where coupler system was true and year made was less than or equal to 1986, it used fi product class desk is less than or equal to 0.7.
And at each step, it chose the path where the mean square error is. Oh, just the mean square error, it's not the root, is highest, right?
7.5 and so forth. Right? So right at the top, we have 20,000 samples, 20,000 rows, right? And the reason for that is because that's what we asked for here when we split our data in the sample.
I just want to double check that for your decision tree that you had there, that the coloration was whether it's true or false, not so like it gets darker, it's true for the next one, not the...
Darker is a higher value. We'll get to that in a moment.
Okay.
So let's look at these numbers here. So in the whole data set, well, our sample that we're using, there are 20,000 rows. The average of the log of price is 10.1. And if we built a model where we just use that average all the time, then the mean squared error would be 0.477. Okay? Okay. So this is, in other words, the denominator of an R squared. Right? This is like the most basic model is a tree with 0 splits. right, which is just predict the average. So the best single binary split we can make turns out to be splitting by where the coupler system is greater than or equal to, sorry, less than or equal to or greater than 0.5. In other words, whether it's true or false.
Okay.
And it turns out if we do that, the mean squared error of coupler system is less than 0.5, so it's false.
And the sample becomes split, which is fair.
Goes down from 0.477 to 0.11, right? So it's really improved the error a lot.
Oh.
In the other group, it's only improved it a bit. It's gone from 0.47 to 0.41.
Wait a second. Mean square error should be less, not more. Well, goldfish brain. Don't blame me.
And so we can see that the coupler system equals false group has a pretty small percentage. It's only got 2,200 of the 20.
Yeah, you can't really do more with the data, which it is doing more with the data, so it's a big split. Yeah. Error less, but the other one more. What was the other one, the thing? There was another thing. Okay.
1,000, right? Whereas this other group has a much larger percentage, but it hasn't improved it as much.
We're trying to
So
improve
let's
both,
say
right?
You wanted to create a tree with just one split. So you're just trying to find...
In the score, yes, I'm still here. In the score, where did I look at it? This is our estimator. I remember I ran it somewhere. Yeah, I can just... Oh, there it is. We want it as high as possible, and it in binary classification we compared to the random classifier. Yes. Here in the print score we have the root mean squared error. I think it's even log, but then this part, it's, I guess, is it accuracy? It's just, he calls it is it all mean squared error? He explained it a minute ago. I can go back, but for now let's see if he explains it more. Okay,
like, what is the very best single binary decision you can make for your data? How might you be able to do that? How could you do it?
Like an example of binary decision would be like, you know, we've studied it multiple times in school when they say in the phone book, you cut it in half and you're like, is the letter I'm looking for like C? Is it in the first part or the last part? Right? I think that's an example we've all learned about.
I'm going to give it to Fort.
Specify the max depth of 1.
But I mean, you're writing. You don't have a random forest.
Yeah, binary
right?
search. Yeah.
How are you gonna like write? What's an algorithm? A simple algorithm which you could use.
Cut by
sure.
half.
So we want to start building a random forest from scratch. So the first step is to create a tree. The first step to create a tree is to create the first binary decision. How are you going to do it? I'm going to give it to Chris. Maybe in 2 steps. Or give it.
So, isn't this simply trying to find the best predictor based on maybe a linear regression?
No.
You could use a linear regression, but could you do something
simple?
Much simpler and more complete. We're trying not to use any statistical assumptions here.
Just cut in half. Sorry. I think that's the most simple thing.
Prince. Oh, of course you're Prince. I knew that.
Can we just do like take just one variable? If it is true, give it like the true thing, and if it is false, go on to
So which variable are we going to choose? So at each binary point, we have to choose a variable and something to split on.
Okay.
How are we going to do that? You want to pass it over there? How do I pronounce your name?
Shikhar. So the variable to choose could be like which divides the population into two groups which are kind of heterogeneous to each other and homogeneous within themselves, like having the same quality within themselves,
but different
and
from
they're very
each other.
different.
Could you be more specific?
Like in terms of the target variable, maybe.
Yes.
Like let's say we have two groups after split, so one has a different price altogether from the second group.
Yes.
But internally they have similar prices.
Okay, that's good. So like to simplify things a little bit, we're saying find a variable that we could split in two such that the two groups are as different to each other as possible.
Okay.
And okay, how would you pick which variable and which split point? That's the question.
I really like this type of teaching where he's giving them nothing in a way. I mean, I guess he's giving them something, but just asking and see where their minds lead them.
Yeah, what's your first cut? Which variable and which split point? We're making a tree from scratch. We want to create our own tree. That makes sense?
Yeah.
We've got some.
But like, I think some students are used to getting more from the teacher.
Over here, Maisley. I'll pass it to Jason, Maisley, maybe.
And he's not like giving up easily. He's not, after two students, not giving them satisfactory answers. He's not saying, okay, here's the real answer. Oh, yeah. Huh. Does he? I've watched some of his stuff, but I guess I don't have that much information about him.
Can we test all of the possible split and see which one has the smallest RMSE?
Formulate the equation. Okay. So when the instructor helps you get to the answer yourself without giving you the answer, that makes you remember the learning far better.
That sounds good. Okay, so let's dig into this. So when you say test all of the possible splits, what does that mean? How do we enumerate all the...
You could invent these formulas if you want through the same thought process. Yeah. Yeah. Wow, inventing even. Yeah.
Possible splits.
Oh, I didn't think of that, but do you want?
For each variable, you could put one aside, and then put a second aside and compare the two, and if it was better.
Good, okay. So for each variable, for each possible value of that variable, see whether it's better. Now, give it back to Maisley, because I want to dig into the better. When you said see if the RMSE is better, what does that mean, though? Because after a split, you've got two RMSEs. You've got two groups.
So you're just gonna fit with that one variable comparing to the others, not so.
So what I mean here is that before we decided to split on coupler system, we had a root mean squared of 0.477, and after we've got two groups, one with a mean squared error of 0.1, another with a mean squared error of 0.4.
So you treat each individual model separately. So for the first split, you're just gonna compare between each variable themselves. And then you move on to the next node with the remaining.
But even the first node, like, so the model with 0 splits has a single root mean squared error. The model with 1 split, so the very first thing we try, we've now got two groups with 2 mean squared errors. You want to give it to Daniel?
Do you pick the one that gets them as different as they can be?
Well, okay, that would be one idea. Get the 2 mean squared errors as different.
But what about the number of samples that's left? You can't just say we have one row left and that's the best one.
different as possible. But why might that not work? What might be a problem with that?
Sample size.
Go on.
Because you could just literally leave one point out.
Yeah, so we could have like year made is less than 1950, and it might...
He gave the same answer as me, and it's making me feel good.
Have a single sample with a low price, and like that's not a great split, is it? You know, because the other group is actually not going to be very interesting at all. Can you improve it a bit? Can Jason improve it a bit?
Could you take a weighted average?
Yeah, a weighted average. So we could take 0.41 times 17,000 plus 0.1 times 2,000. That's good, right? And that would be the same as actually saying, I've got a model. The model is a single binary decision, and I'm going to say for everybody with year made less than 1986.5, I'm going to fill in 10.2. For everybody else, I'm going to fill in 9.2, and then I'm going to calculate the root mean squared error of this crappy model. And that would give exactly the same, right, as the weighted average that you're suggesting. Okay, good. So we now have a single number that represents how good a split is, which is the weighted average of the mean squared errors of the two groups it creates. Okay, and thanks to, I think it was it Jake, we have a way to find the best split, which is to try every variable and to try every possible value of that variable and see which variable and which value gives us a split with the best score.
Wow.
Does that make
Random
sense?
Force does that?
Okay.
Checking everything?
What's your name, sorry? Okay. Easily fixed. Can somebody give Natalie the box and I will take Natalie.
When you say every possible number for every possible variable, like, are you saying like here we have 0.5 as like our criteria to split the tree? So are you are you saying we're trying out every single number for
every possible value, right? So a coupler system only has two values, true and false. So there's only one way of splitting, which is trues and falses. Year made is an integer which varies between, like, I don't know, 1960 and 2010. So we can just say, what are all the possible unique values of year made and try them all. So we're trying all the possible split points. Can you pass that back to Daniel, or pass it to me and I'll pass it to Daniel? Remember, don't speak loudly, step one is breathe in. Okay. Otherwise it's not possible. Physically not possible.
So I just want to clarify again, for the first split, why did we split on coupler system, true or false, to start with?
Because what we did was we used Jake's technique. We
Checking
tried
everything.
every variable. For every variable, we tried every possible split. For each one, we noted down, I think it was Jason's idea, which was the weighted average mean squared error of the two groups it created. We found which one had the best mean squared error, and we picked it. And it turned out it was coupler system, true or false. Does that make sense?
I guess my question is more like, so coupler system is like one of the like best indicators, I guess?
It's the best.
Okay.
We tried every variable and every
so
possible
each
level.
level after that, it gets less and less.
Everything else it tried wasn't as good.
Okay. And then you do that each time you split?
Right. So now that we've done that, we now take this group here, everybody who's got coupler system equals true, and we do it again. For every possible variable, for every possible level, for people where coupler system equals true, what's the best possible split?
And then are there circumstances when it's not just like binary, like you split it into like three groups for like example year made?
So I'm going to make a claim,
Okay.
and then I'm going to see if you can justify it. I'm going to claim that it's never necessary to do more than one split at a level.
Because you can just split it again.
Because you can just split it again. Exactly. So you can get exactly the same result by splitting twice. Okay, good. So that is the entirety of creating a decision tree. You stop either when you hit some limit that was requested. So we had a limit where we said max depth equals 3.
Okay.
So that's one way to stop, would be you ask to stop at some point, and so we stop. Otherwise, you stop when your leaf nodes, these things at the end are called leaf nodes, when your leaf nodes only have one thing in them. Okay? That's a decision tree. That is how we grow a decision tree. And this decision tree is not very good because it's got a validation R² of 0.4. So we could try to make it better by removing max depth equals 3, right, and creating a deeper tree. So it's going to go all the way down, it's going to keep splitting these things further until every leaf node only has one thing in it. And if we do that, the training R² is, of course...
The thing I was talking about was R². It can be, if it reaches 1, then you're good. But the mean squared error has to be low. Okay, there.
1. Because we can exactly predict every training element because it's in a leaf node all on its own. But the validation R² is not 1. It's actually better than our really, really shallow tree, but it's not as good as we'd like. Okay, so we want to find some other way of making these trees better. And the way we're going to do it is to create a forest. So what's a forest? To create a forest, we're going to use a statistical technique called bagging.
So that was just one tree. Man, computers do too much.
And you can bag any kind of model. In fact, Michael Jordan, who was one of the speakers at the recent Data Institute conference here at University of San Francisco, developed a technique called the bag of little bootstraps, in which he shows how to use bagging for absolutely any kind of model to make it more robust and also to give you confidence intervals. The random forest is simply a way of bagging trees. So what is bagging? Bagging is a really interesting idea, which is, what if we created 5 different models, each of which was only somewhat predictive, but the models weren't at all correlated with each other. They gave predictions that weren't correlated with each other. That would mean that the 5 models would have to have found different insights into the relationships in the data. And so if you took the average of those 5 models, right, then you're effectively bringing in the insights from each of them. And so this idea of averaging models is a technique for ensembling.
Yes.
Right? Which is really important. Now let's come up with a more specific idea of how to do this ensembling. What if we created a whole lot of these trees? Big, deep, massively overfit trees, right? But each one, let's say we only pick a random 1/10 of the data. So we pick 1 out of every 10 rows at random, build a deep tree, right, which is perfect on that subset and kind of crappy on the rest, right? Let's say we do that 100 times, so different random sample every time. So all of the trees...
Different random sample, so you give it different data, really?
...are going to be better than nothing, right? Because they do actually have a real random subset of the data, and so they found some insight, but they're also overfitting terribly. But they're all using different random samples, so they all overfit in different ways on different things. So in other words, they all have errors, but the errors are random.
Yes, that's a good idea. It's basically democracy. There's also the I forgot the name for it, but the technique where you ask a group of people and their answer is more closer to the real answer than not. I think there's the one about the weight of the elephant where they ask a group of 200 people and the answer was pretty close. It's like an old thing in math stats textbooks, I suppose. You probably know about it. I think it's just called, I learned about it really recently. Yeah. There's a name for it. I don't think it's ensemble, but the ideas are close.
what is the average of a bunch of random errors? 0. So in other words, if we take the average of these trees, each of which have been trained on a different random subset, the errors will average out to 0, and what's left is the true relationship. And that's the random forest. Okay? So there's the technique, right? We've got a whole bunch of rows of data. We grab a few at random, right? Put them into a smaller data set and build a tree based on that. Right? And then we put that tree aside
and do it again.
And do it again with a different random subset. And do it again with a different random subset. Do that a whole bunch of times, and then for each...
Oh, okay. Wow. Predict the number of hidden emojis in the slide of the lecture. Huh. So you guys actually tested it in real life. That's even cooler.
One, we can then make predictions by running our test data through the tree to get to the leaf node, take the average in that leaf node for all the trees, and average them all together. So to do that, we simply call random forest regressor, and by default, it creates 10 what scikit-learn calls estimators. An estimator is a tree, right? So this is going to create 10 trees. And so we go ahead and train it. I can't remember if I remember to do the split.
I think you did.
Okay, so create our 10 trees, and we're just doing this on our little random subset of 20,000. And so let's take a look at one example. Can you pass the box to Devin?
So just to make sure I'm understanding this, so you're saying like we take 10 kind of crappy models, we average 10 crappy models, and we get a good model.
Exactly. Because the crappy models are based on different random subsets, and so their errors are not correlated with each other. If the errors were correlated with each other, this isn't going to work. Okay, so the key insight here is to construct multiple models which are better than nothing, and where the errors are, as much as possible, not correlated with each other.
Better than nothing.
So is there like a certain number of trees that like we need that in order to be valid? Like,
there's no such thing as like valid or invalid. There's like, has a good validation set RMSE or not, you know? And so that's what we're going to look at, is how to make that metric higher. And so this is the first of our hyperparameters, and we're going to learn about how to tune hyperparameters, and the first one is going to be the number of trees, and we're about to look at that now.
Okay.
Yes, Maisley.
The subset that you are selecting, are they exclusive? Can you have overlapping of them?
Yeah, so I mentioned, one approach would be pick out like...
calling them weak classifiers and strong classifiers and more. Okay, academic version of crappy versus good. Yes. This is pretty academic.
A 10th at random. But actually what scikit-learn does by default is for n rows, it picks out n rows with replacement. Okay, and that's called bootstrapping. And if memory serves me correctly, that gets you on average 63.2% of the rows will be represented, and a bunch of them will be represented multiple times. Yeah. Sure.
Hello. New person. How do I call your name?
So rather than just picking out like a 10th of the rows at random, instead we're going to pick out of an n row data set, we're going to pick out n rows with replacement, which on average gets about 63.2% of the rows will be represented. Many of those rows will appear multiple times. I think there's a question behind you.
In essence, what this model is doing is, if I understand correctly, it's just picking out the data points that look most similar to the one you're looking at.
Yeah, that's a great insight. So what a tree is kind of doing...
Isn't that quite a complicated way of going about doing that, if you see what I mean. There would be other ways of like assessing similarity of features.
There are other ways of assessing similarity, but what's interesting about this way is it's doing it in tree space, right? So we're basically saying what are, in this case, like for this little tree, what are the 593 samples, closest to this one, and what's their average closest in tree space. So other ways of doing that would be like, and we'll learn later on in this course about k nearest neighbors. You could use like Euclidean distance, say, right? But here's the thing. The whole point of machine learning is to identify which variables actually matter the most and how do they relate to each other and to your dependent variable together, right? So if you've, like, imagine a synthetic data set where you create 5 variables that add together to create your dependent variable, and 95 variables which are entirely random and don't impact your dependent variable. And then if you do like a k nearest neighbors in Euclidean space, you're going to get meaningless nearest neighbors because most of your columns are actually meaningless. Or imagine your actual relationship is that your dependent variable equals x1 times x2. Then you actually need to find this interaction, right? So you don't actually care about how close it is to x1 and how close to x2, but how close to the product. So the entire purpose of modeling in machine learning is to find a model which tells you which variables are important and how do they interact together to drive your dependent variable. Okay. And so you'll find in practice the difference between using like tree space or random forest space to find your nearest neighbors versus like Euclidean space is the difference between a model that makes good predictions and a model that makes meaningless predictions. Melissa, do you have?
You queued for a break.
I did, but I feel like we've got only 35 minutes, so yeah.
That was the time for me. She asked for a break. He didn't give it to them because they don't have much time left, but I also I think if I continue, I'll have to continue the whole way, but I think it's a good time for me to try and end this stream. Today was mostly listening, less doing it in practice, because I thought I missed, like, he's still here, he's still in lesson 1, and I thought I missed, so I went through all of this without actually understanding what it's doing, which is okay. Sometimes we make mistakes. It is life. Oh, why did you lose me? Here. Yes. The plan was for me to rename the name of the title to say which lesson I'm in. So like today would be lesson 2, but it's the second live stream that I am doing this. So I'm gonna do that. And yes, I am now like thinking, when should I like regarding the schedule. I don't mind streaming every day, but I know I will need to not like take time off, but like have a day where I'm editing things that may come out of the streams. And I think as of now, I'm just gonna test out how it will be if I stream the whole week. And I know it's not sustainable, but especially if new things happen in my life, the current schedule is fine. I'm gonna try and see if I can edit things during my free time in the weekend, so still do the streams on my scheduled time. That's my current plan. It may change next week, So I'm going to continue because I think I see a good progress on my side, and I like the consistency. Okay. Today was nice. It was fun. Good question. It is a scary process because it takes quite a lot of time. It takes a lot of time. I haven't edited many things in, like, I'd say a year, so I'm a bit rusty, but it's really not that bad. I can trim things down. Like, I like the process. I've been video editing for a while, like even for my personal for personal reasons, but yeah, I like video editing, honestly. Yeah, I remember just testing split screens when I was, I think, in high school because I liked the idea of split screens, two of yourself talking to each other. Yeah, I love the free software called DaVinci Resolve, and I've been using that, I think, since I've had this YouTube channel. Yes, so yeah, anyway, I'm blanking. Yeah, I think the part where I need to, like, find out snippets of my live streams that I can make it turn into something, I don't know. We'll see. I have so many video ideas, but I just don't have I don't know what it is that I don't have to make them. Because, like I said, I can make a video regarding how I am doing this VTubing thing. I think that would be pretty useful for some people. So, and I think most of the time when I need to do something, if I do it on stream, then I actually do it. But if I don't, then I don't do it. And I know I can make that video on stream because of, checking out the different softwares and things and cutting. Yeah, I'll try to put that on my to-do list. My to-do list is actually okay right now. I don't have any PhD related things that I need to take care of, so that's good. Yesterday we brought up an idea taking shorts part of, yeah, basically. Just to turn some parts of the conversation into shorts where it's either useful advice or it's a fun bit of the video, or it just takes time. So I should definitely do it this weekend, because if I don't, then I'll have a huge backlog and I'll be too lazy to do that. I just have to, like, lure myself into doing this, like making myself some coffee, get something sweet, because when you're editing, like, thank you, I like listening to things when I'm doing something that doesn't need my ears, or like when you're doing something that needs your hands, you can watch something or listen to a podcast. But when you're editing, you can't do any of that. It needs your eyes, it needs your ears, it needs your hands. That just proves how lazy I am. Okay. Okay. I think I should go. Yes, definitely. Today was also chill and fun. It was nice. I enjoyed it. We learned quite about the mean root, mean squared, something, log something. And we will definitely be going through the lesson 1, random forest. That one's quite a lot. Yeah. Random forest. Yeah. Yeah, more theory than practice, but I like it. Okay. I will most likely schedule the stream for tomorrow, same time, and I hope you are getting something useful out of this. I hope I'm not wasting your time. Okay, let's end this and come back tomorrow. Today is going to be a busy day for me, so let's see how that goes. Thank you for your time and for helping me understand some of the things. Okay, let's end the stream in starting from 5 to 4 and then 3, 2, thanks, 1, and have a great rest of your day. Bye. Lift off.